So now that we have a fair understanding of how exponential and logarithmic functions work, let's talk about some specific exponential and logarithmic functions. So in this situation, the first one here, we're talking about the natural exponential function. And instead of the value a, we have the number e. E is Euler's number, Leonhard Euler. He's a German mathematician. But e is an irrational number. You have two e buttons on your calculator. One just says e and one says e with a caret symbol. So it will give you the option to raise e to a power as soon as you push it. But e is equal to approximately 2.718. Okay, so we have a special exponential function using that Euler's number, e, as our base. And we have two special log functions. So those also change depending on the base. We can have a natural log, so that is base e. And whenever we have log base e, we're going to write that as ln. In math, we don't write lowercase l's a lot, so they look like 1. I generally write ln, cursive, but some people might want to do a capital Ln. So if your logarithm has a base e, then it's called the natural log, and we write ln. And when we have base 10, that's called a common log. And so if you notice on the notation on the right here, we just have log of x. So if there is no base written, we are going to assume it to be a common log, and we can insert that base 10 in there. So the main thing we want to think about as we move forward is being comfortable converting between logarithmic and exponential form. And if you'll notice here in the bottom, what I'm circling in the purple, we have those conversions. If you've got y equals ln x, that converts to e to the y equals x. And these are if and only if statements, which are biconditional. And if and only if means we can go either direction. We can go from log to exponential or exponential to log. So we've got that conversion. And then the same if we're dealing with a common log, y equals log of x, that would convert to 10 to the y equals x. Right, so this is our conversion formula, and you can write it any way you want with any variables you want, but these are the ones defined by our book. So we've got y equals log base a of x. If and only if goes both directions. A to the y equals x. Okay, so another way that I like to write it sometimes without any x's or y's in there, because sometimes I find that can be confusing. So another way we do this, log base a of b equals c. Well, that can convert to a to the c equals b. So it's the same pattern. And the main thing we're looking at here is we just want to be able to recognize and interchange between log form and exponential form. So for our example, we have 3 logarithms written here, and we want to convert them to exponential form. And the reason this is necessary is because sometimes it helps us understand what's going on better. Sometimes it's a strategy we need to use when we're solving. So when I go to convert this, and another way I like to think about it is this guy goes right in here. So this is the same as saying 2 cubed equals 8, which is a true statement. I don't think I mentioned this yet, but a logarithm, the definition of what a logarithm is the power to which we raise the base to get the argument, and the argument is what's in the parentheses. Okay, so that's the definition of a logarithm. So to what power do I raise 2 to get 8? And that would be 2 cubed equals 8, and that's why 3 was the answer to our logarithm. All right, so our next one here. Notice we do not have a base written. So if there is no base written and it says log, we assume that's a common log, base 10. So that's log base 10 of 1 over 100 equals -2. So converting, it's going to be 10 to the -2 equals 1 over 100. I need to box my other answer over here. All right, and lastly, we have natural log of x equals 1. So this is the same, natural log is the same as writing log base e of x equals 1. And we take that 1 and we pull that over here. Our solution when we convert it would be e to the first equals x. So just as we can convert between logarithmic to exponential, we can go from exponential back to logarithmic. And so, the base in your exponential is going to be the base in your log, and the exponent and your answer are going to switch places. So our first example, 6 squared equals 36. This can be rewritten as log base 6. And then what we want to notice is these two values, the 2 and the 36, are going to switch sides. So log base 6 of 36 equals 2. And so we're not solving anything. We are just converting between forms. So notice the base in your exponent, base 6 raised to the second power, becomes log base 6. And then the 2 and the 36 are going to switch sides of the equal sign. So thinking about that on our next problem here, I'm going to have log base 4. And then again, we're going to switch sides of the 0 and the 1. So this is log base 4 of 1 equals 0. And lastly, we have 10 equals e to the y. So e is my base because e is the value raised to the variable power. So we've got e to the y equals 10. And this would be the same, and if you want to rewrite it, e to the y equals 10, like that, just switch sides of the equation. So this is the same as writing log base e, and then we're going to have 10, log base e of 10 equals y. You'll notice they switched sides there. And when we have log base e, we're going to take that next step because log base e means natural log. We're going to say the natural log of 10 equals y. So I have 3 logarithmic equations that I have written, converting them from exponential form. So moving along, we can find the exact value of a logarithm without using a calculator. You're always going to have your calculator in this class. Nobody's taking it away from you. But in order to know how to deal with logs, we want to make sure we understand what they mean. And so as I said previously, I said a log is the power to which we raise the base to get the argument. And so when we're dealing with a log, that's the same as saying log base, and then the argument is what is in the parentheses. Running out of space there. But a log is the power to which we raise the base to get that argument. Okay? So if we want to find the exact value of a log without using a calculator, we want to think about logs that way. So this first example, 4a, it says log base 9 of 81. Well, 9 to what power equals 81? And the answer is 2. So for B, 5 to what power equals 1? If you raise something to the 0th power, you always get 1. For C, 3 to what power equals 1 over 81? Well, you could think about that as being 3 to what power equals 1 over 3 to the 4th, because 81 is 3 to the 4th. So in this case, we would get -4 as our answer, because that reciprocal property of exponents. On example D, I have log base 10 of 1,000. So 10 to what power equals 1,000? Our answer would be 3. Example E has a natural log. Natural log, remember, is log base E of E. So E to what power equals E? And the only way you get the same thing, raising something to a power, is when the power is 1. And then lastly, for F, log base 4 of 2. Log base 4 of 2, 4 to what power equals 2? We get out 2. So we also have to talk about the domain of logarithmic functions, because if you remember when we graphed those logarithmic functions on the first page, they had a domain restriction. They didn't go to the left and the right forever, right? So the main thing we need to remember is that the argument has to be bigger than 0, okay? The argument has to be bigger than 0 because we have a vertical asymptote at x equals 0. We're never going to touch 0. So in order to find the domain in each of these situations, we're going to take the argument, which is what is in the parentheses, or the expression that we are trying to find the logarithm of, and we're going to need to set that greater than 0. So in part D, for example 5, f of x equals the log of 2x minus 1. We know that 2x minus 1 has to be greater than 0, which add, divide, we're going to get that x needs to be greater than 1/2. And writing that in interval notation, x is in the set from 1/2 to positive infinity. Example 6 here, f of x equals log base 1/3 of the argument square root of 6 minus x. So in this case, the square root of 6 minus x has to be greater than 0. So if we square both sides, that cancels the square root on the left, and squaring 0 still gives us 0. Add the 6 or add the x, either way. I'm going to say 6 is greater than x, which is the same as x is then less than 6. So writing that in interval notation, that would be x is in the set from negative infinity to 6. And then lastly, we would be solving this example 7, f of x equals the natural log of x squared minus 4. Again, that argument, we just know that whatever is in our parentheses, whatever our argument is, it has to be positive. So we're again setting that greater than 0. And this is a polynomial inequality, and we did these in Module 9. So in this situation, we'd factor that. We would get x plus 2, x minus 2 needs to be greater than 0. We'd have two critical values that we could plot, -2 and +2. And if we checked our solution set, where is it greater than 0, we would get positive, negative, positive, choosing test values on each side there. Okay, so in this situation, the solution is going to be less than -2 or greater than +2, not inclusive of those values. So we'd say negative infinity to -2, union 2 to positive infinity. So my three solutions here are the intervals that I have just boxed.